All right, so welcome back. So again, you're getting back your homework number one, traditional homework number one. I do want you guys to go over this thing and look it over. And if you guys have questions, we will be having a review just before our test. I plan on having the test on Thursday, the 22nd, but I'm going to go have the review on the 20th because, well, we will give you back your homework number twos on the 20th and have a chance to go over those things with homework number one. So I'm going to do a homework one and homework two review day on that particular day. So today I'm going to finish up chapters 1.9 and 1.10, a little bit of the work problems and stuff like that. I will be moving on into chapter 2 by Thursday's class. However, I will stop for Tuesday to have a good review day, and your test will be the following Thursday. Okay? So that's our plan. So let's go ahead and get started on today's awesome lecture and picking up where we left off last time. Last time we were working on, the idea of these vectors and trying to get into a feel for, how basically linear transformations, which is what we last talked about, how they affected vectors. You do a vector, you take a linear transformation on a vector, and it has a particular dynamic to that vector. What does it do to that particular vector? Now, one of the things it does is the idea of a projection. So let me give you an example here. And I kind of drew this one up to try to demonstrate with my awesome handwriting. So A is equal to the matrix 1, 0, 0, 0, 1, 0, and then 0, 0, 0. It is a 3 by 3 matrix. And I'll notice on that last row and last column, I have a bunch of zeros. Now, what this matrix is going to do is it's going to take, now, what kind of vector do I have to multiply by a 3 by 3 matrix? It's got to be a 3 by 1 vector. So it's going to have 3 components. So that's a vector from R3. But what this matrix is going to do is going to project R3 onto R2. Let me show you. So it's going to take the classic vector x3 in R3, x1, x2, x3, and then you're going to multiply a times x. 1, 0, 0, 0, 1, 0, 0, 0, 1 times 1, x1, x2, x3, and row by column. x1 times x1 plus 0 times x2 plus 0 times x3 gives you x1. 0 times x1 plus 1 times x2 plus 0 times x3 gives you x2. 0 times x1, 0 times x2 plus 0 times x3 pretty much gives you 0 all the way along the line. So what it does is it takes this three-dimensional vector and only focuses on the first two components and makes the third component 0. Now, it's still a three-dimensional vector, but what it's going to do with the x1 and x2, this is that onto R2. And what we mean by onto R2 is this. So I kind of drew you a picture. So here is your vector right here. It's the classic x1, x2, x3, x vector right here. What applying this particular matrix A times that vector does is it projects it down into the x1 or xy plane or x1, x2 plane if you want to look at it like that. And the vector is only there. It makes the third component, the x3, 0, and so it actually just forces the vector to be perpendicular. Notice that nice 90-degree angle there, slaps it right down, called orthogonal. Orthogonal and perpendicular mean the same thing. Orthogonal is three-dimensional perpendicular, just to make it sound impressive. But it projects it down into the xy plane. There's the vector with just the x1 and x2 components. x1, x2 components. So this is an idea of what a linear transformation will do. It will take a vector, when you multiply it times a matrix, it will do something to this particular vector. In this case, it projects the vector into the x1, x2. It's still the three-dimensional vector. We're still in R3 here, but it only gives you really two components. That's when we say it's going to be quote-unquote onto R2, because it's covering every two-dimensional vector I can think of, even though the third component is going to be 0 for each one of these guys. So here's an example of what linear transformations can do for you guys. Okay, so continuing on, definition. A linear transformation T is a mapping from vector space X to vector space W. Don't worry, I'll go back and redefine vector spaces and all those stuff. But a vector space is a space of vectors like R3 and R2. That's the ones we're going to be focusing on, R4, R55, whatever you want. But it goes, a linear transformation T is a mapping from one vector space, R sub n, I called it X, to another vector space W, R sub m, such that X maps X to W, such that you have two major definitions here. T of vector U plus V is equal to T of vector U plus T of vector V for all U and V in the domain of the T. These are the X vector space. So the first thing a linear transformation will do, when you apply a linear transformation to two vectors being added, that will be the same thing as applying the linear transformation to the first vector plus applying the linear transformation to the second vector. Okay? The second definition, part of a definition of a linear transformation, is what does it do to constants. So you take a linear transformation with a constant times a vector u, the constant c can be held out front, and it's just like taking the linear transformation times vector u and then multiplying by c on it. Constants can be held out front, apply your linear transformation to your vector, and then multiply all the components by c. Only linear transformations have these two properties. A linear transformation, when you do t of u plus v, that's the same thing as t of u plus t of v. And when I do t of a constant times u, that's the same thing as a constant times t of u. So if I give you a particular system or whatever, and I ask you, is it a linear transformation or not? The answer is yes or no, but you only got one shot at this thing. This is what you check. That both these two properties must hold. But there's an equivalent property which is a little bit easier to show. And that is the or equivalent thing here, which says this. Equivalent, if you show me this, in a linear transformation, t of 0 is equal to 0. That will always be the case with a linear transformation. You plug in 0, you will always get 0 out of it. That's what a linear transformation will do. If you don't have a linear transformation, if you got something that 0 maps to 5, it's not a linear transformation. Does that make sense? And the other one is kind of a combination of the 1 and 2 here. If I do a linear transformation of arbitrary constant c times vector u plus arbitrary constant d times vector v, that's the same thing as the constant times tu plus the constant times tv. Linear transformations basically get to distribute across pluses or minuses, and constants get to go out front. That will happen for every linear transformation. Okay? So, c and d are scalars, constant, and u and v are vectors in the domain of t, which is the x, as we set this thing up, the x vector space that we were talking about. Okay? In general, if you have a large combination of vectors, t of c1 times v1 plus c of t2, c2 times v2 plus cn by vn, according to my general linear transformation, I get to distribute that t throughout each one of these vectors, and the constant gets to be pulled out front. This will be equal to c times tv1 plus c2 times tv2 plus plus cn times tvn. We only have to show it for 2, but in general, it'll work for quote-unquote all vectors that you put as a linear combination. This is what we mean by linear transformation. Yes, ma'am. Yes. Well, in terms of proofs, 1 and 2 and A and B are going to be the exact same thing, okay? And so in terms of using a proof, if I want to show that I have a linear transformation, I mean, these are very arbitrary type thing here. This is much more general. And so when I got a linear transformation, or more importantly, I got this system, and I'm supposed to tell if it's a linear transformation or not. First thing I'm going to do is mentally check 0. Plug in 0 in for the 0 vector in for x, and see what the linear transformation or the transformation does to that. But if I get 0 out of it, well then I'm not done. Still may or may not be a linear transformation, but then I'm going to go on to number two. But if I get something other than zero, I'm done. And it's an easy way to show I don't have a linear transformation if it's going to be something quick. It has to satisfy both of them, A and B, or 1 and 2. You got to show both of them. It's usually easier to show the A and B aspect. In my theorem definition, these guys are actually equivalent to another, and this is typically easier to show. Okay? So, with that being said, what exactly does linear transformations do? Well, zeros have to map to zeros. So, you've always got that origin point pretty much staying where it's at. But so an example, and then getting into some of the terminology down here, is this. So I've got this little block of little vectors inside this little block. And what the linear transformation will do, will take this little block and kind of shift it over, maybe extend it out. That's called a shear. Okay? This is that classic shear transformation. But you'll notice the origin will also stay there. It doesn't add up to it, doesn't drop it any. The origin stays the origin, but it will take this block and maybe scale it, shift it around a little bit. That's what they call shear. Another thing a linear transformation will do will be rotate. So I first start out in the X world. I got this little block of little vectors inside this little block. And what my T linear transformation will do will be maybe rotate it like, I don't know, 90 degrees or 45 degrees or some kind of angle that I pick, and a rotation transformation. That's also a linear transformation. Taking stuff, stretching it out and shearing it off or whatever, and rotating are classic examples of what linear transformations will do to a particular set of vectors. Okay? So I'm trying to give you guys more of a visual perspective of what linear transformations will do for you. Now, that being said, let me show you the next page. Yes.
What does it say next to like the graphs?
This one right here is a shear transformation, and this one here is a rotation transformation. These are linear transformations. This is traditionally what they do. Because remember, you still got to be held under this guideline of a linear transformation. The zero vector has to map to the zero vector. So origin will map to the origin, but any kind of vectors going from the origin out will be moved, manipulated, maybe rotated, or stretched out and slanted over. That's the quote-unquote shearing aspect of it. Okay? So, here's one right here. Let's define T going from R2 to R2. Why R2? It's easier to draw. Okay, so R2 to R2 by this transformation. T of x is equal to R times x, where R is a scalar constant. Okay? So we're just doing what we call a scalar multiple. So, a scalar multiple. Now, here's the big deal. We talk about this, basically being a scalar multiple of a constant times vector x. If your constant R happens to be between 0 and 1, if you multiply a number that's a fraction between 0 and 1, it typically is going to shrink it down. Mathematical word for shrinking it down will be a contraction. It will contract it down. If R happens to be greater than 1, we call that a dilation. It's going to expand it off, stretch it out, if you will. We call that mathematically a dilation. So you either have a contraction or a dilation. Well, if R equals 1, that's called the identity, and it doesn't really change the vector at all. But so either you have a fraction somewhere between 0 and 1, or you have a number bigger than 1, contraction or dilation. So I want you to, quote, prove that if R equals 5, then T, this T definition up here, is an actual linear transformation. Well, to prove a linear transformation, I need that definition of linear transformation. So, here we go. Okay? So, here we go. PF for proof here. Let U and V elements of R2 with scalars and D. Okay? These are elements of the real numbers, scalars, just arbitrary constants here. Okay? Remember, we are given that t of x, vector x, is equal to 5 times x. Okay? So, what is t of constant times vector u plus constant d times vector v? What will that be equal to? Don't think too deep in this. The function or the operation is when I take t of x, that will be equal to 5 times whatever the vector is. This is one big vector, right? When you take a constant times a vector plus another constant times another vector, that's one big vector, right? So according to my rule, that would be 5 times c times vector u plus d times vector v. That's the rule. Agreed? Clean that up for me. Now 5 is a constant. How do I do 5 times a constant times vector u plus 5 times a constant times vector v? This is part of our properties of vectors. What can I do with constants? Well, I can distribute them, right? This is just vector math. So this would be 5 times c times vector u plus 5 times d times vector v. Right? Did I lose you guys anywhere there? Now, c is a constant. And I had to explain this to my calculus class not that long ago. It doesn't matter what order you take stuff in when you're multiplying or adding or subtracting. A plus b is the same thing as b plus a. A times b is the same thing as b times a when you're dealing with scalars. Matrices is a different story, but when you're dealing with scalars, these guys are scalars. So I can rewrite that as c times 5 times vector u plus d times 5 times vector v. Because 5 and c are scalars, and scalar a times scalar b is the same thing as scalar b times scalar a. Order doesn't matter. So this would be equal to c times, now, who is 5 times u? Well, vector u, 5 times that would be the same thing as t of vector u plus d, and 5 times v, v is the vector, when you multiply by 5, it's the same thing as the transformation times 5. So what have I just shown you by just playing with arbitrary c, d, and vector u and v, and this linear transformation of tx equals 5x? I have just shown you that an arbitrary t of u, cu plus dv is equal to c of tu plus d of tv. Right? What is that? It's my definition of linear transformation. Also, what would t of 0 vector be? According to the math, what is that equal to? 5 times the 0 vector. And what do you get with 5 times the 0 vector? That means every component is going to be multiplied by 5. But on the 0 vector, every component is 0, and 0 times 5 is 0. So I'm going to get the 0 vector back again. So t of 0 vector is equal to 0 vector. So, putting it up here as t of cu plus dv is equal to ct of u plus dt of v, and as t of 0 vector is equal to 0 vector, therefore, by definition, t of x being equal to r times x is a linear transformation. And here's 2 things I'm doing for you. 1, I'm showing it to you. And number 2, this is probably one of the first proofs that someone has actually walked through with you guys that in a particular math class. don't worry, if you're a math major, we got a lot more math proof classes for you guys to take, especially Math 3163. But this is the idea of a straight definition. The definition, if you go back and look at it, to show you have a linear transformation, you have to show these two things. Or equivalently, you show me that T of 0 equals 0 and T of Cu plus dV is equal to Ct of U plus dt of V. You get those two things, which is exactly what I'm showing you here and here. I can say by definition I have a linear transformation. So, from a picture perspective, if I did this, this is, x, y, two-dimensional vectors here. I'm just going to make a vector here. I'm going to declare this guy to be vector u, and I'll declare this guy over here to be vector v. If I do my linear transformation on that, what exactly does t do to these vectors? U was here. You get 5 times u, and I get 5 times v. That's what t is doing to this vector. It stretches out this way, and t. So this would be, what do we call this? When t is, r, your constant, is bigger than 1, the dilation. We're stretching these guys out, for lack of a better term. We're basically, that's what it doesn't rotate them. It's in the same direction, but you get 5 times that original vector, and you get 5 times the other original vector. It just stretches them out, a dilation. But this is a linear transformation. Does that make sense? Very basic, but we're getting the idea of what linear transformations can do. So, again, terminology. Try this one. This one is a rotation style transformation. And I made it two-dimensional so I can actually draw it. All right, so let's define a linear transformation going from R2 to R2 by T of x is equal to this matrix A times x, or the matrix is 0, 1, negative 1, 0, times your arbitrary x vector. In R2, x vector would be x1, x2. Okay? Now, with this one, let me show you what you get, because linear transformations can be represented by a matrix. That's probably one of the biggest statements I can make for you. When we're dealing with linear transformations can be defined, can always be defined by a matrix. So, here we go. This is my matrix A. So T of x is the same thing as A times x. My matrix A is 0, 1, negative 1, 0. If I multiply row by column, 0, 1, negative 1, 0 times the x1, x2, what do I get? 0 times x1 plus 1 times x2, I get x2 for that first component. Second row, first column, negative 1 times x1 plus 0 times x2. Well, 0 times x2 is 0. Negative 1 times x1 is just negative x1. So what this, quote, linear transformation is doing for me is this. It's going to take the vector x1, x2, and turn it into the vector x2, negative x1. It puts x2 in the first component and makes negative x1 for the second component. Does that make sense? So, here we go. Find the image, again, terminology here, of u, which is going to be the vector 4, 1, vector v, which is vector 2, 3, and vector u plus v. Well, I didn't tell you what 2u plus v was. We're going to find that out under vector t. What would u plus v be? Let's work that one together. What's u plus v? How do you add vectors? What is 4, 1 plus 2, 3? What do you get? 6, 4. How do you add vectors? You add components. 4 plus 2 is 6. 1 plus 3 is 4. Does that make sense? Now, image is what we're after here. So, what would T of u be? That would be matrix A times vector u. What was matrix A? 0, 1, negative 1, 0, times vector u. What was vector u? 4, 1. Well, if you catch the pattern on what's going on, you can just write it out, but I can do matrix multiplication. Row times column. 0 times 4 plus 1 times 1 is 1. And negative 1 times 4 plus 0 times 1 is negative 4. So, T of u would be, the image is 1, negative 4. What would, put it over here, what would T of v be equal to? That would be the matrix A, which is 0, 1, negative 1, 0, times vector v. Vector v is the vector 2, 3. What do I get there? Row by column, 0 times 2 plus 1 times 3 is 3. Row by column, negative 1 times 2 plus 0 times 3 is negative 2. I get the vector 3, negative 2. Does that make sense? All right. Yes, question. Yeah. What's that now? Well, I'm actually showing you this matrix does exactly that. It's swapping the components and making the second component negative. It's swapping the components and making the second component negative. That's what this matrix is doing for me. Okay? I'm going to draw it in just a second, but I'm trying to show you the question is, what's the image of TU? The image is 1, negative 4. What is the image of TV? It is 3, negative 2. Does that make sense? Now, what would T of u plus v be? Well, that would be 0, 1, negative 1, 0, times, what was u plus v? You guys did that one for me. Was it 6, 4? And what do I end up getting? Row by column, that gives me 4. Row by column, I get negative 6. But if you look at this, wouldn't that be the same thing as T of u plus T of v? What is 1, negative 4 plus 3, negative 2? 1 plus 3 is 4. Negative 4 plus negative 2 is negative 6. So, and the reason why I get this is because I even told you, T was a linear transformation. Now, what exactly is going on this guy? So, here, let's take a look at this guy. Let's take a look at vector u. What was vector u? Vector u was the vector 4, 1. And I'm going to start introducing some stuff to you guys just because it saves a lot of time when I'm typing up a test. I could also write this as bracket, a little pointy bracket, 4, 1. I can write it as a column vector or a row vector. It's just a vector, okay? So these guys are equivalent, just a little notation, but sometimes it's easier to write it in a little bracket, 4, negative 1, takes up less space on paper and stuff like that. So, let's plot that guy, graph him. 4, 1. 1, 2, 3, 4, 1. Start at the origin. 4, 1 is here. You start the origin and then you project out to that point. This is what vector u is. This is how you would draw vector u. Well, we start at the origin, and basically you can look at these vectors as components, you know, x, y, or, you know, uv, whatever you want to talk. All right, so now, what was T of u equal to? We did that one. T of u was equal to what? 1, negative 4. Let's graph that. X is 1, y is negative 4. 1, 2, 3, 4. There's negative 4. 1, negative 4 would put it there. You start at the origin, and then you project yourself out this way. Here is T of u. Okay? And just to show you, let's come over here and do the same thing to V. What was vector V? Vector V was 2, 3. So 2, 1, 2, 3, 4, 1, 2, 3, 4, 2, 3. X is 2, y is 3. Here is vector V right here. What is T of V? T of V is 3, -2. 1, 2, 3, -2. 1, 2. Here's -2, here's 3, here's that point. There's that. So this is T of V. What seems to be the relationship between what is T actually doing? It's taking these guys and rotating them. How much? 90 degrees. It took this guy and rotated it 90 degrees. So this linear transformation that we're talking about, where that T was represented by the matrix A, which is 0, 1, -1, 0, actually ends up taking my vectors and literally just rotating them clockwise, 90 degrees. Okay, that's what's going on with this guy. Does that make sense? So this is the dilation or contraction, rotation. This is what linear transformations can do for you guys, okay? All right. Linear transformations can be represented by matrices, and one of the things, if you don't want to do anything to a vector at all, you're going to basically multiply it by the identity matrix. So, we're going to define the identity matrix, which is the I n by n. It'll be a square matrix where you have ones on the diagonal and zeros off the diagonal. When you multiply this matrix times any vector that's of correct size, you're going to get the same vector back again. Okay? Let me show you. If this is my identity matrix, 1, 0, 0, 0, 0, 1, 0, 0, all the way down. Ones on the diagonal, zeros off the diagonal. If you multiply by x1, x2, x3, out to xn, row by column, you can get x1. Second row by column, you get x2. Third row by column, you get x3. All you're going to get is those components each time. So you get the same thing back again. It's called an identity matrix. Whenever I multiply and get the exact same thing back again, that's called the identity. Under multiplication, the identity is 1. What's 1 times anybody? Anybody. Under addition, the identity is 0. What's 0 plus anybody? 0. Think about it. 0 plus anybody would be anybody. So you have an identity under addition and identity under multiplication. This is the matrix multiplication identity. Okay? So, in terms of linear transformation, see where I'm going with this. We're going to define a linear transformation T going from Rn, that's the reals, components coming from the reals, of size n or n components, going to Rm by the taking vector x from Rn and multiplying it by matrix A times x. So, what size does A have to be? Again, I want you to follow the size thing here. This is Rn, so this is an n by 1 vector, right? This is going to be an n, it's the same vector, n by 1. What size is matrix A if you're going from Rn to Rm? Very good, it's m by n. Remember what we talked about in terms of how to multiply matrices times other matrices or other vectors. Row by column has to match up with the row by column. The columns have to match up column by whatever the next number is going to be for your next component here. So the ends end up matching up and canceling. So AX would be m by 1. M by 1 vector is in the Rm vector. So look at the description of how the mapping goes and the description of the matrix. T goes from Rn to Rm. What size matrix is that? M by n. It's in reverse in the way we write the mapping. So if you're going from vectors Rn to Rm, the matrix that's going to do that is going to be an m by n matrix. That's what the linear transformation matrix representation is going to do that. And The transformation is completely determined by what T does to the columns of an n by n identity matrix. Why is that? This thing's n by n. If you look at the columns, you've got 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, bunch of zeros, 0, 0, 0, 1, bunch of zeros. If you look at the columns, each component individually is going to be represented from x1 all the way down to xn. Okay? So here's that concept of looking at the matrix and then looking at the columns here. So a transformation is completely determined by what T does to the columns of the n by n identity matrix. So, a little side note here. With this, when you look at this particular column, this first one is going to be called E sub 1, E sub 1 column. The second column is called E sub 2. The third column is called E sub 3, dot, dot, dot. The last column is called E sub n. What's the deal? This is in the math notation thing here. You see that subscript? That's the component on your vector where the 1's going to show up. Otherwise, everybody else is 0. So E1, the first component is 1, everybody else is 0. E2, the second component is 1, the first component is 0, and the rest of them are 0. E3, the 1 shows up in the third component, and the rest of them are 0. En, everybody is 0 except the last component, the nth one is going to be a 1. So, here's the deal. If I give you this, now don't think too deep, but there's a pattern for this is what I'm going after here. All right, so T goes from R2 to R3 such that I'm telling you that E1 is going to go to the vector negative 2, 1, 7, and E2 goes to 5, 0, 3. Now, we're talking about R2. What is the identity matrix in R2? R2, the identity matrix would be I of 2 by 2. What would the identity matrix of a 2 by 2 matrix look like? 1, 0, 0, 1. So this is E1 is 1, 0. E2 is 0, 1. The size of the matrix, I went m by n. This is arbitrary. This is actually 2 by 2 here. So 1, 0, and 0, 1. So T of 0, 1 goes to 2, 1, 7. T of E2, T of the vector 0, 1 goes to 5, 0, 3. Okay? Where again, the identity here is a 2 by 2, it's squared 1, 0, 0, 1. So E1 would be 1, 0, and E2 would be the second column vector, which is 0, 1. So, I want you to find T of x and write a matrix A such that Tx is equal to a matrix A times x. I mentioned to you guys before, any linear transformation, if it's a true linear transformation, has a matrix representation for that transformation. That's why we always say Tx is equal to A times x. This time, I'm asking you to find what A is. All right. So, here we go. Step 1. Okay? Let's talk about an arbitrary x vector. Now, we're talking about this guy as an element of R2, which means my x vector is going to have to be two-dimensional. We'll just call him x1, x2. Does that make sense? But I want to write him as a linear combination of the column vectors of the identity matrix. So this would be equal to x1 times 1, 0 plus x2 times 0, 1. Agreed? How do you add vectors? Well, x1 is going to be a scalar times 1 plus x2 scalar times 0. So that's just going to give you x1. And then the second component is going to be x1 times 0, which is 0, plus x2 times 1, which is x2. Okay? So what this really is this x vector is really x1 times the vector e1 plus x2 times the vector e2. This is e1, this is e2, as we defined it up here. Now, Once you've written it like such, now, here comes your step 2. Take t of x. What would that be equal to? Well, that would be t of x1 e1 vector plus x2 e2 vector. That's just substitution. Here's the important part. T is a linear transformation. What does that mean? You have a linear transformation. We have a definition. So when I do t of a constant times a vector plus a different constant times another vector, that's equal to the constant times t of the first vector plus the second constant times t of the second vector. So according to being a linear transformation, this would be equal to x1, because x1 is a constant, t of e1 plus x2 t of e2. That is using the definition of a linear transformation. See where this is going with in our chapter 1.9 stuff here. Okay? This is going to be equal to x1 times, this guy was defined. What was t of e1? T of e1 was the vector -2, 1, 7. -2, 1, 7. Plus x2 times, what's e2? E2 was 503. Okay, so who is this guy equal to? Well, how do I multiply scalars times vectors? This you just do it component-wise. This is -2 times x1 plus 5 times x2. This would be x1 plus 0x2, if you think about it, because that's 0. And then 7x1 plus 3x2. Now we have this vector of, like I've written as a system of equations type thing here. But if you write it as a matrix, the vector x that you're talking about multiplying by is x1, x2. What would the matrix be? You know, row by column, but I want a 2x1 plus a 5x2. So this would be -2, 5. I want a 1x2 and a 0, sorry, 1x1 and a 0x2. That would be a 1 and a 0. And a 7x1 and a 3x2, 7, 3. So this is the matrix A that's going to represent that linear transformation. Now, I made something actually quite trivial, difficult, because I was trying to show you something. It's the pattern here. Have you seen these guys before? -2, 1, 7, 5, 0, 3? Well, that was that t of e1, 2, 1, 7, and t of e2, 5, 0, 3. So, what we're really saying here is that note that the matrix A is going to be column-wise t of e1 vector and then t of e2 vector. And basically, you know, these are your components. And if I had more components, I could have put them out here. But that's exactly what's going on. You're putting the vectors, the t of e1 and t of e2. This is how you're going to create the matrix A that represents your linear transformation. Okay? Yeah. What are you talking about? Number this one? What? This? Where? Oh, this right here. This is no. That's an arrow. Okay. You see these little bars right here? You talking about that? Yeah. Okay. How do you write a vector? And how do you know the difference between a vector and a scalar? So, great question. But you've got to know. Understand. This is introduction to linear algebra. Everything has a symbol in this stuff. You see this guy right here? Is that a scalar or a vector? What is it? How do you know? All right. What's the vector symbol? So this would be a scalar, this would be a vector. So I'm putting these little arrows above it so you can denote that E1, that's a vector, okay? It's not gonna be some kind of scalar. This is a scalar without any kind of little symbol above it, but that's a little vector, you know, a little arrow pointing into a direction. That's the standard notation for what a vector is, okay? So here's the difference between the two. So when you're actually looking at what I'm talking about here, those little guys are actually little arrows above it, letting you know that these guys are actually vectors. X1 doesn't have that above it, right? That's a scalar. That's a scalar. But this vector over here, vector x, see that guy? That's a vector x. That's x with a vector. And the vector x is going to be this x1, x2. That has the little bar above it. This one doesn't. So it's a subtle notation, but it is a very important notation to distinguish between these guys. So, here we go with this. Theorem. Now, all this was to build a theorem here, but again, you're getting into higher level math classes on the concepts of how do we actually declare something special here. Here it is, theorem. T going from vector space Rn to vector space Rm is a linear transformation. Then there is a unique matrix A. Any linear transformation can be written as a matrix. There's a unique matrix A such that T of x is equal to A times x for all x in Rn. And A is going to be m by n. See that Rn going to Rm? We talked about that a few seconds ago. The matrix is going to be m by n. Catch patterns on this stuff. Where A is equal to T of E1, T of E2, T of En. These T of these E guys end up being the columns of the actual matrix. So what you need to do is identify where does your, what we call the elementary vectors come from. 1, 0, 0, 0, 1, 0, 0, 0, 1. Where do these guys map to? And that's going to help you define what your matrix is going to look like. This is what we call the standard matrix for a linear transformation, okay? Now, with these guys, we have some other operations and things like that. Now, I came up a little while ago, a special example for you guys where I took a particular vector and I rotated him 90 degrees. You with me? Now, let T go from R2 to R2. So I'm only talking about the two-dimensional because it's so much easier to draw. And I want you to represent this matrix A by this. Matrix A is going to be the cosine of phi, negative sine of phi, sine of phi, cosine of phi. And look what happens when I take that matrix. You pick phi. Phi is an angle, okay? T of x would be equal to A times x, which is A times, this is two-dimensional, x1, x2. So if you've got an arbitrary x1, x2 vector out here, it's going to rotate it, and this will be counterclockwise phi, whatever that angle happens to be, to this T of x vector. This is a rotation vector that will rotate it theta degrees, or theta radians, whatever it is, in a counterclockwise fashion. So this is a rotation matrix. And this is awfully helpful in terms of you want to particularly rotate vectors around and still getting linear transformations. Now, a lot of people have a tough time trying to remember this particular matrix because it's awfully helpful when you're trying to do some kind of rotation of manipulating vectors or whatever. When I write down a vector, I look at it like it's an ordered pair. X comes first, Y comes second, XY. Now let's talk trig for a second. In terms of trigonometry, what trig represents x coordinates? What trig represents y coordinates? What represents x coordinates? Cosine. So this would be the cosine, pick your theta. I would put phi's on this one. You can talk about it being theta. And y's would be sine. okay? That goes in the first component, okay? What comes in the second component, help me out here. What would x prime be and y prime be? Since you all had calculus before, I assume you guys know how to do this. What is the derivative of cosine? Sine of theta. What's the derivative of sine of theta? Cosine of theta. This becomes your second column. Does that make sense? So what you got going on here, just to give you guys a feel for this, this would be x, y, and then x prime, y prime in terms of your sine cosines. This is where this guy was developed. Well, what it really does is it takes whatever vector you got and rotate it phi or theta, radians or degrees, whatever, that amount of that particular angle, and points it in the other direction. Magnitude would be the same, but the actual angle is based upon what you decided for phi to be when you plug it in. Okay? Again, this is awfully helpful with this stuff in terms of manipulating these particular vectors, because I want to show you something rather than I did copy this one out of the textbook because I didn't want to draw it. But I want to show you what, again, these are 2 by 2, so it's easier to actually focus on and stuff, of what these matrices, these 2 by 2 matrices can actually do for you. Okay? So, all right. I got this x1 and x2 axis. I typically call them x and y, but they're going to call it x1 and x2 because you never know what world you're going to be playing with and stuff. So, what does a reflection through the x-axis, x1 axis? X1 axis is your x-axis. So any vector up here will be flipped down here to the, basically from the first quadrant to the fourth quadrant. The matrix that will be standard matrix, which is your representing the linear transformation that does this, will be the matrix 1, 0, 0, negative 1. It will take any vector up here and basically reflect him across the x1 or x-axis down below into from the first quadrant to the fourth quadrant. All right, if you want to reflect through the x2 axis, which is also known as the y-axis, you've got any vector over here, you want to reflect it across the x2 or y-axis, that will give you this matrix here, negative 1, 0, 0, negative 1. Negative 1 in the second row, second component going through the x1 axis, but in the first row, first column position when you want to rotate around the y or x2 axis. Okay? Keep on going. If you want to rotate, or reflect, if you will, reflect through the x1 equals x2. x1 equals x2 is that line that splits the first and third quadrants. You want to take stuff over here and flip them up here, and take stuff over here and flip them down here. This is the matrix that does that. It's 0, 1, 1, 0. It basically, it takes the identity and flops this guy and flips this guy. The identity was 1, 0, 0, 1. Now it's going to be 0, 1, 1, 0. But now what happens if I want to reflect any kind of vector across the x2 equals negative x1 axis, which is that angle that's going through the second and fourth quadrant. Any guy up here wants to flip down here, and any guy down here will flip up here. That will be just taking this matrix here and making all the ones negative. So this would be 0, negative 1, negative 1, 0. The famous flipping it or reflecting it across the origin. Now, across the origin means, you got a point over here. It's going to literally go across the origin and over here. And this is the matrix that does that. It's negative 1, 0, 0, negative 1. This reflects across the origin. If you remember, reflecting across the origin is like the odd function aspect from your college algebra days and stuff. Keep on going. I got more of these guys for you guys. Okay, contractions and expansions. What these basically, that's just the basic 2 by 2 matrices can do for you is this. You've got this K0, 0, 1. This will actually take this horizontal contraction. So it's going to take whatever vectors and either, if K is a fraction between 0 and 1, it's going to contract it back to closer to the x2 axis, or it's going to expand it if K is bigger than 1. So your block is still the same, but it's either going to pull it in or push it out. look at this matrix, K0, 0, K0, 0, 1. If you want to vertically contrast or expand, push it down or push it back up, it just switches the component. It's 1, 0, 0, K, and if K is a fraction, it pushes it down towards the X1 axis. If K is bigger than 1, it pushes it up. And the last two I want to talk about here is the idea of shearing, okay? And it's the idea of the horizontal shear, which basically takes any kind of block and either shifts, basically shifts it to the left or shifts it to the right. And it depends on whether K is negative or K is positive, but that shearing aspect gives you the matrix 1K, 0, 1, and this would be the horizontal shearing left to right. This is the vertical shearing up and down, and basically if K is negative, it pushes it down. K is positive, it shifts it up. K shears it up, and that would be the matrix 1, 0, K, 1. So it's interesting on how the K and 1s and negative 1s play a part to see what these guys do to vectors in terms of the linear transformation stuff. Just giving you guys some visual perspective of what this stuff can do for you. Okay? So, more definitions, as if you guys don't have enough, but I warned you guys about an introduction to class. So, definition. DEFN, definition, math guy. All right, a mapping T going from Rn to Rm is onto, or surjective. Surjective is the traditional word for it. You guys probably know better as onto. Is onto Rm if each vector B in Rm is the image of at least one vector of X in Rn. I.e., for each B in Rm, you can find an X in Rn such that T of X is equal to B. So let me slide this down for you just a little bit. And let me see if I can draw you guys a picture. All right? So, here's what you got. This is the wonderful world of Rn. This is the wonderful world of Rm. And T is your linear transformation that maps from this world Rn to this world Rm. To be onto or surjective. Surjective meaning onto means I can pick any vector over here in Rm. Any vector you want over here in Rm, and there's going to exist. There exists an X vector in Rn such that of X is equal to that U vector. In English, what I'm saying is this. When I'm talking about surjective or onto, you got a domain and range. Let's go back to old school days of codomains, and we can get fancy on the terminology. But this is the range, basically, right? You can pick anybody in the target of where the vectors are supposed to go. Any vector over here in Rm, and there's guaranteed you got some guy's going to map to them. That's what we mean when we say it's onto. Any guy over here in the target of your linear transformation, the range, anybody in that range, there's going to be somebody in the domain that's going to map to them. T of X is equal to that arbitrary V that you found over here in Rn. That is onto, or surjective. Next one is a mapping RT going from Rn to Rm is one-to-one. Fancy word for one-to-one is injective. If each B in Rm is the image of at most one vector X in Rn. Okay, i.e., if T of X is equal to B, there exists no other X vectors, call if Y is in Rn such that T of Y is equal to B. So one-to-one. Don't think too deep when we come up with names for the injective for the fancy word, but one-to-one means this, okay? Rn, Rm. you see this x vector over here? He's gonna map, let's call him this v vector right here. And that's it. V is equal to t of x. And nobody else can map to this guy. Does that make sense? One vector maps to one vector, because this is what we mean by when we say 1 to 1, injective. If I could have something like this. Here is a b vector over here. Here is an x vector, here is a y vector, and they both map to the same guy. This is not injective. Not 1 to 1. One vector to one vector. That's what we mean by 1 to 1. Multiple vectors mapping to a single vector over here in range, that can't happen, okay? I'll give you an example. For example, you think of functions. We'll go away from vectors for a second. But functions. Y equals x squared. Plug it in. What is 2 squared? What's negative 2 quantity squared? 4. Y equals x squared is not 1 to 1. There's 2 different x values mapping to a y value. That's not 1 to 1. To be 1 to 1, one x gets to map to one y. And once that guy is mapped over, nobody else can map to him. That's what we mean when we say it is 1 to 1 or injective. Okay? So, quote, uniqueness. If t of x vector is equal to some matrix A times x vector is 1 to 1 injective, then ax equals b has exactly one solution, unique solution, or no solutions. Not 1 to 1 means we can have multiple, we can have multiple solutions, okay? So, 1 to 1. You're either going to have a solution or maybe no solution. You won't have an infinite number of solutions. So now we're talking about, okay, 3 ways when we start about solving matrices. 3 ways. What are the 3 different types of solutions you can have with matrix, with systems of equations and looking at them as matrices? You can have consistent, unique. What does that mean? There's only one answer. You can have consistent, infinite. How many answers is that? Infinite number. You can have free variable stuff. You pick what the free variable is, and you can basically from that figure out how many different kinds of answers you can get. And then what was the last case? No solution, which is called inconsistent, right? So when you happen to have a 1 to 1 case, when you got matrix A is going to be 1 to 1, or linear transformation T is going to be 1 to 1, injective. Then that equation, when converting it to a matrix, AX equal to B is either going to have one solution, and it's going to be a unique solution. You know, x1 equals 5, x2 equals 7, x3 equals negative 23. You get one solution. Or you could actually have that no solution case, okay? That doesn't mean it's not going to be 1 to 1. That means that, I'm sorry, the B that you chose, nobody actually is going to be mapping to it. Does that make sense? We never said it was going to be on to. We're just talking about 1 to 1. So you either have one solution or no solutions. You're not going to get the multiple solution case. Does that make sense? Multiple solution case means there's lots of different vectors going to that one particular B answer. You won't get that with a 1 to 1 case. So, here we go. And again, I'm throwing stuff at you guys that I will not put on your test, proofs, but I have to do proofs to be legitimate to my math major friends, that we have to start introducing the concept of proofs in a linear algebra class. So here's another one. Theorem. We're going to prove it. And again, this is the first class that we know, and we don't make you guys do this stuff on test, but in our lectures, we do want to introduce the concept of a theorem and actually how to prove it, so you're at least have seen one. Okay, theorem. T is a linear transformation going from Rn to Rm. Then T is 1 to 1 if and only if T of x equals 0 has only the trivial solution. And remember, what is the trivial solution? What does trivial solution mean? Everybody's got to be 0. Who's going to map to 0 on a linear transformation? You're guaranteed 0 maps to 0. But if you got a linear, that's part of our definition. T of 0 equals 0. But maybe you could have another vector mapping to 0. Not if it's 1 to 1. If you got 1 to 1, T of x equals 0 only has the trivial solution. You won't have another solution with free variables or anything like that on there, okay? But things I want to kind of focus on with you guys in the last 3 minutes I have in class is that word if and only if. Mathematically, and for you computer science majors out there, what does if and only if mean to you from a logistics perspective? If and only if. Biconditional. Very good. That means it's a two-way implication. That's what if and only if means. So if I got 1 to 1, I get T of x equals 0 has only the trivial solution. If T of x equals 0 has the trivial solution, then automatically I get 1 to 1. It goes both ways. Does that make sense? So to be able to prove a biconditional, a two-way if and only if, you got to prove it both ways. And basically when you do this way, you're basically given, P implies Q. You give yourself P and then you got to show Q. All right, so here we go. Given T is a linear transformation, and it is an T is 1 to 1, okay? Then T is a linear transformation means, by definition, who is T of 0 going to be equal to? Part of that definition. Who's T of 0 equal to? 0. Okay? Thus, x must be equal to 0. And we've gotten that condition over there. We got the trivial condition. X got to be 0. But so the big one is going to be going this direction. Give yourself the other stuff. T of x is equal to 0 has only the trivial solution. Okay? This means T of 0 has got to be equal to 0. That's the trivial solution. X has got to be equal to 0. If T is not 1 to 1, there exists a vector A and a vector B, elements of Rm, such that there exists vector u and vector v and Rn, again, such that, again, equations, T of u, sorry, there exists, bad word there, vector b, I only want one of them, vector b, sorry, put it up here, you guys can see this, vector b, element of Rn, such that T of u is equal to b, and T of v is equal to b. But T is a linear transformation. Thus, who is T of u minus v going to be equal to? This is the quick, sharp part of it. By a linear transformation, what do you get to do with a linear transformation? In lack of a better term, you get to distribute them. Who is this going to be equal to? T of u minus T of v, right? But T of u is equal to b minus T of b equals b. What's b vector minus b vector? 0 vector. Okay? Thus, T of u minus v is equal to the 0 vector, implying u minus v has got to be equal to the 0 vector. Who maps to the 0 vector? U minus v. Thus, vector u equals vector v, which means only one vector does it, t is 1. And there's your proof that, if you got going the other way, you're going to get that quote unquote one-to-oneness. One vector only maps to one vector. Okay. Last thing before I let you guys go, the only other thing that I wanted to do today, we're going to get these proofs in here that I did not get to, which you guys needed for your test, was this. And I want to pass this thing out to you guys if I figure out what I did with it. There it is down here. I wanted to look at one of these problems right here, okay? It's the circuit problems. And I didn't get a chance to do this one today, so I'll do it next time. So we'll do 2 circuit problems next time. Before you guys turn in your homework set, I believe you got a circuit problem for me. I want to help you guys go over that one because you never know when you're going to see it. So I want to do this problem, and I'll help you out with that last homework problem that you have on the homework set, okay? So I'm going to pass these things out to you guys because this will be the one that we're going to pick up next time. So tell you what, pass one of these guys out to everybody, if you don't mind. And we got one question. Yes, ma'am.
So we need to have higher homework 2 done except for the circuit problem?
Pretty much. Yeah, I'll help you out with this one right here because I didn't quite get to actually show you how to set up the equations. And we'll use our calculator to help us solve it and stuff like that. So, yeah, but the trick is basically Ohm's law, but another way of setting up the system of equations and applications. Because the trick is, voltage is equal to current times resistance. So you got to basically look at your current over the resistance and how these guys link up. I'll show you how to come up with these equations and stuff. Study hard, and I'll see you guys on Thursday.